Hello, everyone. Welcome back to Historical Geology 1404. Today is lecture 7. You are going to be getting one more lecture in this module on Thursday. And then next week, 1 week from today, is our Exam 2 review, and Exam 2 will open. All right. You have had 3 labs assigned at this point. Various discussion boards, or if you are in my online class, Go React participations. Please make sure that you are keeping up with your assignments. I've already had some drama go down with grade reports. I understand when students are dissatisfied with their grade report, but really the only thing that I can tell them is you should have gotten the work done before I had to report your grade, right? It's unfortunate when I have to say that, but it's the truth. And there's nothing that I can do about it unless you want me to put a false grade on your report, which I will not do, right? The best advice I can give is keep track of when your school pulls grade reports. It's usually 3 days after they require me to turn them in. So if you get grade reports on Friday, I usually am required to have those grades into your school by Wednesday. So don't wait until Thursday night expecting that you're going to get the grade report on Friday for whatever your grade is when you turn it on Thursday night. First of all, it's pretty inconsiderate to me to expect me to come in on Friday morning, bust out all your stuff before you pull your grade report. And second of all, that's not how it even works. They pull it on Wednesday. Okay. So I come in on Wednesday, make sure that I'm caught up on grading as much as possible. And then you get the report from Wednesday on Friday. So just keep that in mind. All right. Let's see, what else? Yeah. Have I graded exam 1? Yes. Yours hasn't been graded. Did you turn it in towards the end of the due date? Did any of you get exam 1 grades? Yeah. You did? Yeah, I was like positive I did it. Okay, then yours was probably just on the tail end. I probably graded everyone else's before the due date was up, and you turned yours in on the later. Yeah, that's fine. I'll get to that as soon as I have a spare minute here. Anything else? No? Who's excited for Thanksgiving? I'm getting excited for Thanksgiving. You are?
Yes.
What's your favorite part of Thanksgiving?
Eating.
Eating, of course. Yes, that's classic. Do you stay here or do you go somewhere?
Sometimes we go to Mexico. Sometimes we stay here.
Mm-hmm. Is there such a thing as a cultural Mexican day of Thanksgiving? Or is that just like you have like a dozen holidays that are all about that, I feel like, right? Yeah.
We just go over just to visit.
You just go to visit and
Yeah.
Okay, cool. I know like Canadians have a different Thanksgiving day than us. My wife is half Canadian. She has dual citizenship, so sometimes we celebrate both. Cool. Yeah, I like Thanksgiving because my nearest family, like my family, my parents and my brothers and sisters, they all live way up north in Idaho. My wife's family is all over the place. Her nearest family is 10 and a half hours away in Phoenix. So we don't go anywhere. We stay here and we have a giant Friendsgiving. So it's usually like 20 or 25 of all our friends. We all pick a dish and get together and have a fun meal. It's a good time. Play board games afterward. It's a good time. I'm looking forward to it. Okay. Let's get to it. Lecture 7 today. We are taking what we have learned about life and stratigraphy and combining it together. Okay. This is when you are getting a little bit more information about the geologic record and how we interpret things about the geologic record through the changes that occur in life that we observe in those layers. All right. Now, before we can get started on actually discussing how to correlate, let's talk a little bit, let's give a little bit of credit where credit's due to the guys that put a lot of time, their entire lives in some cases, into figuring out how this can be used, okay? Setting the stage for all of this, okay? Nicholas Steno. Nicholas Steno, born in 1636, okay? Died at 50, which back then was a pretty good ripe old age, right? He was a scientist at first. What I mean by that is he actually spent his time, observing, collecting information, trying to come up with rational explanations. Towards in the last, half of his life, he kind of changed gears a little bit and became a clergyman. Very interesting. A lot of people look at this transition as, oh, he gave up on science. I don't think that's necessarily the case. I think that through his pursuit of science, he may have found cause to believe in something bigger. And I don't think that that necessarily goes against science. All right. But he got a lot of bad press for that, I guess you could say. But he was instrumental in establishing the principle of superposition. Who can tell me what that is? Remind me.
The lower, the oldest.
Yeah, older layers are on the bottom, newer layers are on top. Okay, he was very instrumental in putting that together, figuring that out. Also, original horizontality. How likely is it that a substance is going to stay in one place if it is not near or perfectly horizontal? Like, if I have a surface that's on an incline, how likely is it that things are going to roll off that incline? Pretty likely, right? Angle of repose, you remember that conversation from 1403, right? It's the maximum angle at which an object can be at rest without falling under the influence of gravity. Well, if it's at horizontal or even just near horizontal, stuff is going to stay in that spot, and therefore sediment will eventually become a sedimentary layer in that orientation. So the law of original horizontality basically states all layers of sedimentary rock, no matter what angle they are at now, they could be vertical, but when they were deposited, they were originally horizontal. Okay, that's the law of original horizontality. And then he also theorized a lot about where fossils came from. At this point, remember, this is the 1600s, right? How old did everyone believe the Earth was?
Just like a million.
Huh?
5 million?
No.
7,000?
No, 6,000, right? You remember James Ussher in, what was it, 1620, something like that?
Oh,
Yeah. Said the Earth was formed in October 22nd at 9:30 a.m., 4004 BC.
You're not going to believe it, but I saw a comment of a few people that were debating that the Earth was 7,000 years old.
Yeah, where?
On Instagram.
On Instagram? I would expect nothing less from Instagram.
I was like, oh my God, no way these people.
Yeah. And you had a good time listening and laughing to them, didn't you?
They were saying that it was proved by scientists.
Yep. This is the thing with science. There are a couple of ways of looking at science. You can look at science as a means to an end, or you can look at science as the pursuit of truth, right? If you look at science as the pursuit of truth, then you're never fully satisfied with the answers you get, because you always want to get better, more resolved answers. And you're consumed with the desire to keep looking, right? If science is a means to an end for you, then you come with an idea already in mind. You cherry pick the science that fits what you think the world should be like, And that's what you say to people. And anytime people disagree with you, you're like, no, 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 but this. Fully ignoring all the stuff that says otherwise. Those are the people that view science as a means to an end. Unfortunately, that's most politicians and a lot of other people, right? Science as a means to an end is flies in the face of what science is really meant for, right? At least in this humble scientist's opinion. So yeah, people who say the world is flat, the earth is 7,000 years old, and there is science to prove it, they may have cherry-picked 5% of scientific observations to support their theory, but they're ignoring 95% of the rest of it because it doesn't conform with their worldview. That's not the way to use science. So that's what that is. It's fun to listen to them argue, though. I don't know if I've recommended this to you or not yet, but I believe it's still on Netflix. There's a documentary called Behind the Curve. Yeah, it's about flat earthers and why they believe what they believe. It is hilarious. Highly recommend. If you want a good laugh this weekend, put on Netflix and look at Behind the Curve. Yeah.
Did they spend like thousands of dollars trying to remake an experiment and then they proved the curves?
They did. They did. This is a little bit of spoilers for the documentary, but they spent a lot of money to make an experiment to prove that they could see a light across the curvature of the earth. They were like, sure, the curvature of the earth. We are going to build this light so bright, and someone that far away where you say the earth is curving away is going to be able to see our light. And they did their experiment, spent a bunch of money on it, did their experiment, and it failed.
Even if it was flat.
And then they were like, okay, we must have done it wrong. At no point did they say, okay, the earth must be round. They said, we must have done the experiment wrong, and it kept failing.
And then one time they were like, okay, but if you put it up a little bit.
Yeah, what if you increase the height? Well, by increasing the height, you are acknowledging that there is a curve that you need to get your light over, right? It's funny to watch these things. Anyways, I try not to rag on other people's worldview too much unless it impinges directly on my own. So I'm going to stop there.
That's fine. I think they made a weather balloon or got a weather balloon, flew it out just to see like Earth curves as well.
Yeah, there's plenty of weather balloon footage. Of course, they say that is fabricated. Most of the people that I know who believe the Earth is flat also believe that the moon landing was fake. And so the pictures coming, right, because we had CGI in the 60s. If they go out of their way to try and prove that CGI technology existed, I'm just like, how about Occam's razor? How crazy is it that the most simple explanation, you know what Occam's razor is? Occam's razor is the most likely answer is the simplest answer. Okay? The more complex and convoluted an answer is, the less likely it is to be true, right? So how crazy is it that for these people, they have to come up with explanations so complicated that man going to the moon is more simple than their explanations? That's like, that should tell them something, but it doesn't. Anyways, moving on. William Smith was an English surveyor. How many of you know what a surveyor is? Yeah.
He just looks at the land and like draws it on a piece of paper, right?
Looks at land, draws it on a piece of paper. Okay. That's kind of like a cartographer.
He asks
right?
people.
Huh?
He asks people.
He asks people questions. Okay. So he's not conducting a survey of the population. He's not doing a social experiment. That is, I mean, you are correct. That is one definition of the word, I suppose. But I'm talking about like a geosurveyor, a geographical surveyor. Very similar to what you were saying. Yes, there are maps involved, absolutely, but it's not just making maps. A surveyor's job is to measure distances and allocate space for projects. So have you ever been going along the highway and and you see those guys standing at the median or at the side, and they've got a tripod with a device, and this guy's looking through the device, and he's looking at this guy who's holding like a flag a couple 100 meters down the road, right? Those are surveyors. They are measuring out distances precisely for a future project, probably in that case, a highway expansion, or maybe an off-ramp for the highway that they're going to build there, right? They're measuring out for some sort of project, and because the distances need to be precise, they have to mark them on GPS. Now, back then, I mean, we're talking 1700s here, right? 17 and 1800s, no GPS, right? So you're right. He did all his work on maps, but that wasn't his making maps, wasn't his entire job. So he was an English surveyor, so he would go around the English countryside, really all over Britain, and he would work on all these projects. Normally, when you want to build a thing on the ground, you have to move ground to build that thing, right? Dig up rock, blast through hills, cut your way through a mountain. And so as he was on all these projects, he started to notice that the same layers of rock would show up across different parts of the countryside. He would see, oh, that layer of rock looks like the same layer that I encountered on this project 100 miles that way, right? So that's when he started tracking all this stuff. Where am I observing the same layers of rock? Where are they popping up? At what elevations are they, right? And then it didn't take long for him to realize that some layers of rock shared the same fossils as others. And so he started tracking that as well. And he kind of put two and two together, so to speak, and realized, okay, well, if this layer of rock over here has this fossil, and this layer of rock over here has the same fossil, they must be from the same time. And using this information, later on in his life, he was able to construct the first geologic map. That's a picture of it right there. The first geologic map of England, where each color is coordinated for a certain age of rock. And this is the exact same process that we use today to make our own geologic maps. Okay? So studying the layers of rock and the fossils present in there, the changes that he could observe very simply, just with his eyes and the limited communication that he could have with other geoscientists around. Remember, he was not educated as a geologist, not initially anyway, okay? It's something he kind of fell into through his observations, right? Through all of these things, it gave us a tool so useful that we still use it today, almost 300 years later, okay? Now, unfortunately, he was on his deathbed before anyone actually, it was widespread enough for people to actually acknowledge his contributions. So he didn't get to see too many accolades for that, but we're talking about him in my class right now. So good for him. Georges Cuvier. In case you couldn't tell, he's French. He was a naturalist, which, can anyone remind me what a naturalist is? We talked about this a little bit in 1403. Before we had what we consider to be our modern day cut and dry scientists that use the scientific method and all of that. Huh? Well, he did use some scientific like techniques and whatnot, but a natural philosopher is kind of a slightly different thing. That's a long, long time ago. That's like Aristotle sort of stuff, right? A naturalist. A naturalist is someone who is multidisciplinary, okay? So I call myself a geologist. What does that mean? I have lots of experience in geology and education in geology. And yeah, it branches out a little bit because my specialty is paleontology. I know a lot about biology, and I know a little bit less about chemistry and a little bit less about physics, but still enough of those to get by with, right? A naturalist is someone who has studied physics, chemistry, biology, geology, and all of it, okay? Well-rounded jack of many trades sort of scientist. That's what a naturalist is. Naturalist studies all sciences in the natural world. So not really an expert on any one thing, but great at all of them, if that makes sense. Okay, so French naturalist. Now, the idea that fossils were from animals that had been dead for a long time had kind of bounced around the community before. But he was one of the first people to actually publish major theories about what could have caused so many animals to die. Now, he did it from the perspective of catastrophism. He absolutely was on the Earth is 6,000 years old boat. Okay. But he did some important work in saying, well, maybe there were some incredibly catastrophic events that killed off all of these things all at once. Okay. The idea of an extinction hadn't really shown up yet in literature. That so many of God's creatures could die all at once seemed pretty incredible. However biblically supported it could be. I'm sure you're all familiar, at least in concept, with the idea of Noah's flood, right? An account in the Old Testament describing the world, or at least the perceived world of the person who wrote the account, becoming flooded in some giant event that killed off everyone but Noah and his family and the animals that managed to survive on their boat. So what would you call that except an extinction level event, right? And so with this knowledge in mind, he theorized that there are these incredibly massive events that periodically would kill lots and lots of animals throughout Earth's history, even though, you know, that history was only 6,000 years old in his view, right? So however wrong he was about the timeline, the whole concept of extinction events largely stemmed from his work. So we do owe him some thought there. And then there's James Hutton. You remember Hutton? Principle of uniformitarianism. Give me the principle of uniformitarianism.
The geological processes that happen today also happen in the past and will happen in the future and other planets.
Okay, yeah, that's a condensed version. Does anyone have the full version? In your notes, perhaps, if not memorized.
Physical, chemical, and biological laws that operate today also operated in geological past.
Yeah, physical, chemical, and biological laws and processes that occur today also occurred in the geologic past
And will occur now.
and will occur in the geologic future
And somewhere.
and are occurring everywhere else, right? We have absolutely no reason to believe that laws that operate here don't operate the same way in other places, with a few possible exceptions to that rule, like proximity to black holes, where things get really weird, right? But that's a subject for a different class. All right, so James Hutton was not the first person to propose such an idea, but he was the first person to kind of put it in a way and with data that finally made a huge impact in the scientific community enough to get it accepted. Okay. So all of these gentlemen, and by the way, I know I only listed men here, but there are tons of women that contributed to this as well. Okay. Theory of plate tectonics, right, often is associated with Alfred Wegener, but there was a woman named Marie Thorpe who did a lot of the legwork for that, and often isn't all that often, attributed. It's not all that often attributed to her, but she did a lot of the work that led to the current theory of plate tectonics. So I know I haven't listed any here, but honestly, it's more because of a lack of time than anything. All right. All right. So I think we did this exercise back in 1403, but let me just refresh your memory here about how we break up geologic time. Here we have a whole bunch of events that occurred in our lifetimes, assuming that you all learned how to ride a bike and went to school, right? Safe bet that you were born. The rest of those things, I guess I'm not really sure, right? So if we put all of the dates associated with it, we have our biological events here that have occurred in our lifetime. The numerical dates for when they happened, with 0 being what we call current era, BC and BCE. Are you all familiar with that? Okay. And then there's our sequential time, which we label in groups based upon those biological events. So in this example, my life before I started school, I have simply called the pre-Schoolian, and my life after I was in school, I just simply called the Schoolian. By the way, notice 3rd grade is here, but 1st and 2nd is not. Those are not data points I have here. I simply left them out. Think of those as parts of the fossil record, right? I have no record for being in the 1st and 2nd grade, but I do for being in the 3rd grade. And so that is where my Schoolian time begins. Make sense? Okay, so here's our geologic time scale, time intervals, numerical time, and sequential time. Eons, eras, periods, and epochs are separated by these biological events, right? It's probably kind of hard to read on my screen here, but you have a copy of this on your PowerPoint. So like here, the first amphibians, here, first reptiles, here, marsupials, here, first mammals, so on and so forth. With eons being the largest interval, eras being the next, and by the way, those are there are 3. Okay, we have the Precambrian, excuse me, the Precambrian, which is kind of considered before life. Okay, the Paleozoic, okay, is an era. Precambrian is an eon, and the Phanerozoic are eons. Okay, then you've got the Paleozoic era, okay, which is going from Cambrian to Permian. Kind of think of that as initiation of life all the way up to dinosaurs. So the earliest forms of life leading up to dinosaurs. And then from Triassic to the end of the Cretaceous is the age of dinosaurs. We call it the Mesozoic era. Really, when you think about it, Jurassic Park should have been called Mesozoic Park because they had Triassic, Jurassic, and dinosaurs in there. They called it Jurassic Park. But it wasn't just Jurassic dinosaurs. That's a little pet peeve that all paleontologists share. We all love Jurassic Park. It just should have been named Mesozoic Park. And then the Cenozoic era, which we currently live in, picks up where the dinosaurs died off all the way up to now. We are living in the Cenozoic era. Then we have periods. Our eras are separated into periods: Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene, Quaternary. Then we have epochs, okay? There are lots and lots and lots and lots of epochs throughout all these periods, but the only ones that are relevant to us that we are going to discuss are the Carboniferous, being broken into the Pennsylvanian and Mississippian, and the Cenozoic era ones. So the Paleogene is made out of this Paleocene, the Eocene, and the Oligocene epochs. The Neogene is made out of the Miocene and Pliocene, and the Quaternary is made out of the Pleistocene, Holocene, which a lot of people have started calling the Holocene the Anthropocene. You know what that means? What does anthro usually reference?
Like spider?
Huh?
Like spider?
Expires?
Spider.
Spiders. No, that's arthro. Huh? Hmm?
Back.
Everyone, yeah, people, humans. Putting anthro on anything is kind of a reference to humanity, okay? When I say anthropomorphizing, that means I'm putting a human personality on a thing. The Anthropocene, they're trying to change the name of the Holocene to the Anthropocene, and a lot of people have already accepted it to designate that this is the time period that we really started having an impact in changing our planet, either through overhunting, establishment of civilizations, fossil fuel burning, all of these things that we've had a massive impact on our planet. That's why a lot of people have started calling this the Anthropocene, because we represent a large enough change to our planet and its biological ecosystems that we could have our own, chapter of geologic time. Even though, I want to put this in perspective for you, by the way. If I took this geologic time scale and I stretched it end to end across the football field, furthest part of the end zone to the furthest part of the end zone, humanity would only have existed as a civilization for the thickness of my fingernail, the width, not this, at the end of one of those end zones. Okay? I want to put that in perspective for you. But we've already had such an incredibly powerful influence on our world's systems that it's probably becoming justified to name a time period after us. Although I do think it is a little bit of human hubris to name a whole geological time period after us, but
We on top of the food chain.
we are on top of the phylogenetic tree, right? We deserve our own time period. Gosh darn it. Okay. All right. So how do we break apart these geological boundaries? Well, we've learned a couple of ways already. Lithology change, right? Different type of rock, limestone, sandstone, clearly different types of rock. Let's give them different names. Call that a boundary. Cool. What about if it's the same rock, sandstone, sandstone? Under what circumstances would I separate those as different formations from each other? Something has to be different. If it's not something different in the lithology, it's got to be something like maybe fossil content. So fossil A is present in the first layer, but fossils A and B are present in that second layer. Because that's where B starts, I might draw a boundary there. Okay? That's where its fossil record begins. I cannot, for 100% certainty, confirm that's where that species began. It could have been living a long time before, but simply not fossilized. Or I could just simply have not found the fossils yet. But I can only work with the data I've got. So that's where I draw that boundary. Okay? So the things that can cause us to create those boundaries using fossils, a change in abundance. What does that mean? How many of a thing are there? Maybe I have a layer of rock that I found 1 or 2 trilobite fossils in, and then 10 feet above that is a layer of rock that is so full of trilobites that, it's like I'm pulling them out of the rock by the handful. Okay, there are places like that. They're really cool. Where I used to live in Ohio, there was a dam spillway nearby, and the local rock would weather into the spillway. And I'd go walk on that spillway, and I'd pull trilobites and brachiopods and crinoids and all sorts of stuff. I still have tons and tons of that material in my boxes in my storage room. Yeah, there are places that have so many fossils, like the entire rock is seen to be made out of fossils. So an example of this would be a change from the Precambrian into the Cambrian. Okay, so right here, we call this entire space the Precambrian. This represents the vast majority of geologic time, by the way. 4.54 billion years to 541 million years. That's 4 billion years of history that we have condensed into about 8 inches. Why?
We don't know.
Okay, there's a lot we don't know about it. Absolutely true. It's really old rock. Most of it is either not at the surface or not accessible. What else? What else was there not a lot of or any of?
Records of fossils.
Life. Right? The oldest evidence we have of life, possibly, is here in the Archean. Okay? Very likely started in the Archean, but we're talking bacteria. Single-celled organisms for a while. And then multicellular algae. They don't leave a lot of fossils. There wasn't a lot of diversity. So all the way up to here with the Cambrian. At the Cambrian, that's where we see an explosion in diversity of life. Sponges show up, right? All sorts of crazy looking animals, okay? And so because that's where the fossil record really takes off, that's a change in abundance and in diversity that led to the end of the Precambrian and the beginning of the Phanerozoic, okay? We already talked about William Smith earlier. Okay. Stratigraphy. You already have had an exercise in stratigraphy with Lab 2. Stratigraphy is, this is the definition I'm going to give you, the partitioning and study of geologic time in distinct lithologic units. Now, I taught you in that exercise how we differentiate them from each other based upon what? What characteristics did we use to separate the layers of rock in our Lab 2? What were some of the observations you had to make or interpretations you had to give?
If there were like waves, right, or like just the physical condition of the rock,
What do you mean by physical condition?
like what it looks like.
Which is based upon?
Weathering.
You can't tell anything about weathering. We're talking about a piece of paper, not a sample. What pieces of data were relevant on that lab?
The environment.
We didn't discuss the environment on that lab.
The grain size?
The type of rock, okay, yeah, things like grain size, but that's relevant to figuring out what type of rock you're looking at, right? Okay, the type of rock, huge factor. What else did we make note of there? We didn't actually discuss time periods on that. We could have, but we didn't.
Grain size.
That's a property to help you figure out what kind of rock it is. What other things did we make note of? Was there any bedding structures? Yeah. What are the fossils? What do we call these things? Structures, right? Sedimentary structures. The type of rock and the sedimentary structures are what you used to differentiate, to tell the difference between these layers of rock on a sheet of paper. We do the same thing with them in real life, okay? Stratigraphy. Now, just because we only use the rock type and the fossils present to tell these layers of rock apart from each other does not mean that that is the only way that we do it. As a matter of fact, there are many other ways that we use stratigraphy to tell them apart from each other. I'll talk about more of those in a second, but first, correlation. Anyone want to take a crack at explaining what correlation means? What does it mean to correlate something? To correlate several things.
Find similar things.
Yeah, compare similarities, make them match up. So how can I correlate a layer of rock here to a layer of rock in Wyoming?
Fossils.
Things like fossils and chemicals and all that stuff. Different types of stratigraphy. but correlation is the act of doing that, okay? So different ways, different types of stratigraphical analyses we can do to line up these layers of rock, to correlate them. Chronostratigraphy. So if I'm interested in studying just rocks within a certain interval of time, I can line them up based upon the time that they were deposited. Chronostratigraphy, only the ones that are relevant to each other in the same time period, okay? Biostratigraphy. This is a study that I can do, a method of correlation using only biological remains in those rocks. Fossils, primarily. Trace fossils can help as well. So if I was going to do a biostratigraphical study, I would want to identify as many fossils as possible in the layers of rock that I am interested in correlating. And where I find them adding up, matching up, that can be very useful. Here on this example here, you see I've got two particular layers. Let's call these two layers of rock for the purposes of this exercise, okay? Where you see the arrows pointing down, that means that that species was already existing, right? It started off somewhere further down before coming up into these two layers that we're interested in. Where you see the species, where you see these arrows pointing up, that means that they continue beyond this top layer. But what do you notice? A lot of these species that had been alive for a long time, once you hit this line, this boundary, this interval between these two layers of rock, what happens to a lot of them? They disappear, probably indicating that, yes, they died off. Far fewer species continue upward. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 species continue up. Where we started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, that had existed before. And then 1, 2, 3, 4, 5, 6, 7, 8, that exist only within this time period. So 24 species existed in that time period. But once we hit this boundary, only 10 continue on beyond it. What happened? Something. This is what a biostratigraphical study can help us determine. There was some kind of an extinction there, probably caused by an environmental change. Now we can investigate what kind of environmental change because we know there was one. Okay? Biostratigraphy. Now for this, we use index fossils. Remember that index fossils are the ones that we identify that match certain criteria to be very useful for correlation. What are those criteria? It has to have been alive for a short duration. It has to have an abundant population. Why abundant? Well, the more animals or the more organisms, more individuals of that species that were alive, the more likely it is that they will get fossilized, right? Then they need to have a widespread habitat. If they were in a very small confined location, that's not very useful for correlation, is it? But if I have species A in Portugal and species A in Brazil, I can correlate those layers a lot easier, okay? And then they need a unique physiology. Why? Because we need to be able to tell them apart, right? If Angel and I were both reduced to skeletons at this moment, it would be very difficult for you guys to tell us apart by our skeletons. They would look extremely similar. But what about my skeleton and a chimpanzee skeleton? What about my skeleton and a bat skeleton? My skeleton and a whale? My skeleton and a lizard, right? The more uniquely different the physiologies are, the easier it is to tell them apart from each other. Magnetostratigraphy is something that we discussed actually in 1403, where I told you that every now and then our magnetic fields switch, right? You remember that? When our magnetic fields switch, magnetically inclined iron minerals form oriented towards wherever magnetic north is at that point in time. So right now, magnetic north is in the northern hemisphere. At some point, it's going to switch and go to the southern hemisphere, and any new iron minerals that are formed at, say, mid-ocean ridges are going to be oriented that way. So because we know that this happens through time, I can look at these older layers of rock that have these magnetic minerals and see what orientation they are pointed in. And that tells me how old it is, first of all, and also what the magnetic field orientation was like at that time, where they were geographically, all of these things. Okay. And then lithostratigraphy, which, is just by rock type. Easiest one. That's the one that you guys did in your lab. Okay. By the way, this is what magnetostratigraphic column looks like. If I was going to give you a stratigraphic column and correlate magnetostratigraphy with geologic time, this is what it would look like. Okay. So this is the Paleogene down here. Here's the Paleocene. Here's the Cretaceous. So dinosaurs died right here. And going up this section all the way to modern day. Okay. Where each black and white sequence is either magnetic north is up in the northern hemisphere, or magnetic north is in the southern hemisphere. Each one of these sequences we call a chron. Okay. That's why they're C5, C5a, C5b, C5c. Chron. That's what that C stands for. So what methods have people used throughout the years to try and figure out how old the Earth is? Well, there have been some really fun ones. Okay. For example, people tried doing that math based upon how long it would take the ocean to become salty. What's the problem with that?
That they need salt.
Right. Salt is an extremely common ionic bond. So they're assuming there wasn't any salt to begin with, but there was all that water. That's a very, very, very flawed assumption, right? So that one doesn't work. And then how long does it take for the Earth to cool off? What's the problem with that one?
It's not heated right now.
It is very heated right now. Earth is very hot inside, well, like the outside where we live.
Assume that the Earth was originally hot.
Okay, but it's pretty safe to assume that the Earth was originally really hot, right?
But that it cooled down.
And it's true that it has been cooling down. The problem here is not with that Earth started hot and has gotten cooler.
Maybe they assume that it got that it, I don't know, like it was a straight line upon this to coolness.
Perfect. They assumed a uniform cooling rate. If that were true, then the Earth's surface and the Earth's center would be the same temperature today. It's not. Why? Because there's a huge compositional difference. The material at the center of our planet, very radioactive, very dense, generating a lot of heat. The material on the outer surface, very light material. Those 8 elements that we learned make up 92% of our Earth's surface. Very light, non-radioactive, far less dense. Okay, there is a compositional difference and therefore a non-uniform cooling rate. And so you cannot use cooling rate of the Earth to figure out how old the Earth is. Also, there's the fact that the material inside our planet moves, generating frictional heat, keeping that heat going further and further. Okay. Radioactive decay. What's the problem with that? That's fine. Think away.
Like when you mean radioactive decay, like
Unstable isotopes to figure out how old the Earth is. What's the problem with that? And is there one?
each mineral has like different times, like each atom.
Okay, so when a rock is formed with radioactive elements, the radioactivity of those elements is what we use to determine how old that material is. Okay? There's not really a problem with that. That's the way that we use to figure out how old things are, actually. Okay? That's what we've settled on. Radiometric analysis. Okay? So, because we know how long it takes for radioactive isotopes to decay, right? For example, carbon-14, 5,730 years, okay, and it becomes nitrogen-14. Uranium-234, 215,500 years. Uranium-235, 704 million years. Uranium-238, 4.6 billion, so on and so forth. Because we can see this happening in real time and record it, we can use that to figure out how old things are that contain those things. Okay? There's some crazy ones. Rubidium-87 has a half-life of 48.8 billion years. You won't even reach one half-life in the current age of our universe. Our universe is about 13.7 billion years old as far as we can tell. Right?
I feel like I can see it.
Yeah. A full half-life for this hasn't even passed yet for our universe. But it's still measurable. We can still measure it. Okay? So because these are consistent and measurable, that's our most common, reliable method for determining exact dates of things. Fossils are useful for relative dating. But with radiometric dating, that's where we get actual times from. Years. Event stratigraphy is something occurred that was large enough, intense enough to leave a record of that one single event. For example, a layer of volcanic ash from a volcanic eruption present in layers of rock. That is a marker bed, we call that. Okay? Asteroid impacts often leave layers of dust bearing exotic minerals and exotic metals like iridium. Iridium is extraordinarily rare on Earth, but there's a lot of it in asteroids. And so whenever we find a layer of iridium-rich dust in a layer of rock, we know that's corresponding to some giant asteroid impact. Actually, the layer of dust that was full of iridium from the comet or from the asteroid that killed the dinosaurs, scientists knew about that long before they ever found the crater from that impact off of Mexico. Okay? And only after discovering that crater, actually it's really funny, an oil company found the first evidence for it. And I know two of the guys that were on the expedition that went and found the crater itself. This is back in the late 70s. They
Like a big hole in it.
Yeah, off the coast of Yucatan. That's where the crater that killed the dinosaurs, from the asteroid that killed the dinosaurs is. It's called the Chicxulub crater. It's huge, by the way. But yeah, they found this layer of iridium-rich material that corresponded to an asteroid impact, but then didn't know about where that asteroid impacted until decades later when it was found off of Mexico. Okay? And then there are unconformities. Unconformities represent erosional events. Okay? And there are several different types. Disconformities look like this, where you have layers of rock, right? Deposited, deposited, deposited. And then this erosional boundary. It's obvious that at some point deposition stopped, weathering and erosion took over and removed some material, making this uneven surface. And then deposition started again. That layer, that layer, that layer, right? That is a disconformity. Then we have a nonconformity. So we have igneous or metamorphic rock here that has been weathered and eroded and then deposited on top, making these horizontal layers. A paraconformity, these are tricky. These are really tricky because you have layer, 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 flat boundary, layer, layer, layer. How do I even know that's there? It's not uneven. It's not an erosional surface. How do I know it's there at all? What if that's 20 million years old and that's 7 million years old? That's really the only way I could tell, right? There is some missing time there that I can only see by analyzing that rock and that rock, okay? So at some point, deposition did stop, but there was not a significant amount of weathering or erosion that took place before deposition started again. That's a paraconformity. And then an angular unconformity. This is when you have tilted layers of rock. So remember, these were originally horizontal, but some tectonic event has caused them to be tilted at this angle. Then they got weathered down, and then new material was deposited on top. That is an angular unconformity. So these are marker beds. These are marker units that we can use to describe, okay, a thing happened here, a thing happened there, a thing happened here. Volcanic ash. So like this is the Long Valley volcano right there on the border of Nevada and California. It erupted right there a long, long time ago. But because of the prevailing wind direction, the ash got blown all over these states. Matter of fact, we have some here in our layers of rock, okay? And that layer of ash that we have here correlates to the same one we have in Colorado and Utah and Wyoming and Arizona and Nebraska from this one volcanic eruption. Marker beds, okay? Those are just some examples of marker beds. One small event or large event that we can correlate across a large distance. So some uses that we have for correlation. We can take, this is just in the oil field, for example. It's the best example I can give for our area, right? If we take a seismic profile, which remember we get by blasting sound waves underground and seeing what wavelengths reflect back to us and at what frequencies, right? We can make a seismic profile like this using that seismic data. And then I can drill holes and pull up miles and miles of core, okay? This isn't miles and miles. I'm pulling up some here and some here and some here and some here, okay? Tons and tons of core. And I can compare those core and make a stratigraphic column from those core samples. Then I can overlay my stratigraphic column that I made. So here's my stratigraphic column that I made using those core samples. And I can overlay it on top of my seismic profile like this. And I can see that sandstone lines up with this dark line. That limestone lines up with this white line. That shale lines up with this dark line. And using that information and my knowledge of where oil tends to congregate, where it tends to collect, what type of rock we usually find it in, I can figure out the most likely situation on this profile for where my oil is. Okay, that is correlation. I can compare this column to that column, and I can see where the same layers go across. Look, at this sandstone, I can follow the sandstone line all the way down here to where it lines up there. Okay, so if I find oil in that sandstone, I may find some here. But then again, the oil probably flowed up that way from here to begin with because it is up this unit. And the oil is flowing to try and get to lower pressure. Where's the lowest pressure? At the surface. I'm more likely to find oil up there in this high zone than I am in this low zone. Using those little pieces of information that I know, I can make a reasonable guess for where my company can drill for oil, and I can make them hundreds of millions of dollars, right?
How much they earn, people that do this?
Petroleum geologists, it's one of the highest paying jobs you can get. I know several petroleum geologists that make in excess of $200,000 a year. I know a guy who did it for about 40 years and is a millionaire. He teaches college where I got my master's degree. He doesn't have to. He could retire. He still does consulting on the side, and he teaches because it's fun. But, you know, he wears a suit every day. He's got the nicest car I've ever seen in my life. He's a VIP at every society and every club. And yeah, he's a real cool dude. But I mean, he's a millionaire. He doesn't have to work. He just wants to.
How many years of study is that?
To become a petroleum geologist, you would need at least a master's degree these days. And then before you could get to the point where you're making that big money, you really need to prove yourself. So you would start at the bottom with some company like ExxonMobil or Chevron, just working as part of a team. And then if you can prove that you are adept at making these interpretations, your team lead is like, wow, this guy really knows what he's talking about. You probably get promoted in 4 or 5 years. Eventually you become a team lead, maybe after 7 or 8 years. After a decade, you have a name for yourself. The other companies know who you are, that you have a great track record for finding oil. You become competitive. People want you. They're willing to offer you tons of money to leave your current company to come work for them because you have a great track record. That's where this comes in. You just work your way up the ladder. I make 150 grand at this company. Well, we're willing to offer you 200 grand. You're in. I got you. I'll be there on Monday. You know, that's how it goes.
I'm gonna do this.
You're gonna do it?
I'm gonna do this.
All right. Y'all heard it. He finally admitted he's gonna be a geologist. And on the day Lydia's not here, what a shame. Someone has to tell her. All right. So one of the other cool things that we can tell by looking at the stratigraphy is how the temperature has changed on Earth. Temperature cycles. A few things can affect this. Okay, we already learned about the Milankovitch cycles, right? The eccentricity, obliquity, and precession of the Earth as it moves around the sun, right? Its elliptical orbit, its angle, and its wobble around that angle, right? All affecting, we call those Milankovitch cycles, and they all seem to affect how much light Earth absorbs, how much is reflected, and therefore how much heat is absorbed into our systems. Does it cool off? Does it heat up? Do we enter an ice age? Do we leave an ice age? All of that are affected by the Milankovitch cycles. When a cycle begins, it often triggers what's called a cascade effect or a positive feedback loop, okay? So if we start to cool off, our snow line drops. Our snow line drops, more glaciers form. Our glaciers form, our albedo, which is our reflectivity, increases. Our reflectivity increases. We reflect more light. We don't absorb more light. Things cool off more, and the snow line drops even more. Positive feedback loop, okay? And that's what cascades into an ice age. On the other end of that, things heat up. Volcanoes spit out greenhouse gases. Plants die, and because plants die and don't absorb as many greenhouse gases like carbon dioxide, they tend to build up in the atmosphere. Humans figure out how to burn fossil fuels and release extra carbon dioxide and other greenhouse gases in the atmosphere, right? Whatever the cause may be, these greenhouse gases stay in our atmosphere. They prevent the loss of heat through the atmosphere as that radiation from the sun tries to leave. Earth heats up, snow line increases in height, goes further up in elevation. Glaciers melt, albedo drops. We do not get as much reflected light, and so more of it stays on Earth because of the greenhouse gases. Boom, bada boom. We end up with a super hot Earth. It goes back and forth, and it has for so long. The oldest ice age that I can think of that we have in the geologic record is 2.6 billion years old, I think. This isn't new. Ice ages, global warming, it's not new. We didn't invent it. We can't give ourselves credit for that. It's been going on for a long time. This one, yeah, this one's, like I've said before many times, we didn't start it. It had already begun, but we gosh darn are finishing it, right? We've added so much significantly to it that we cannot deny the fact that the intensity is on us. The advent of this global warming event is not on us. The intensity will be on us, though. which is what we're trying to figure out how to control or at least survive. Other things we can tell through stratigraphy. Sea level changes. How can we tell if the sea level changed? By the types of sediment that are deposited, right? You know by now that there are certain types of sediment and therefore sedimentary rocks that will result from that sediment that are deposited in deep water, shallow water, and continental environments. We can tell that by the type of rock and the structures present, as well as fossil content. So knowing that, I can use stratigraphic columns through drill holes and such to reconstruct a transgressive regressive sequence map. What is that? Transgression is when the sea levels rise and the land gets flooded. Regression is when sea level falls and so the oceans get lower and continental material can be deposited further out into the ocean. And so as you go up through geologic time, you can see transgressive, regressive, transgressive, regressive, okay? So right here, look at this. This is beach sand. This is shale, and this is limestone, okay? So if I can see a sequence of sand and then ocean floor and then limestone, right? It's like deep water and deeper water out there, right? If I can see that sequence, I know I'm looking at a transgressive sequence. Ocean levels are rising, pushing the beach further inland, right? If I see shallow sediments with deeper sediments on top, that's transgressive. Deep sediments with shallow sediments on top is regressive. So here we have a regression, right? Where I have lagoon on top of barrier island on top of deep ocean. Transgressive, barrier island on top of lagoon on top of beach. And then both. There's a transgressive and then a regressive, okay? Transgressive, ocean moved in. Regressive, ocean moved out. Real world example. Here's a cross section of a chunk of Europe. Paris sits right here on this map, okay? This is the surface, okay? So you can see, first of all, here's an unconformity, right? That's what that looks like, okay? So we can see where we've got, right here, you can see this is our terrestrial sediment, and then the yellow is the marine sediments. So going back through time, where Paris is now was under a lot of water not long ago geologically. That part of the Europe only came up out of the water when Africa started moving north and Europe kind of got shoved up out of the ocean as Africa is crunching its way into Eurasia, okay? So not that long ago, where Paris is now was under a lot of water, okay? And then there was a regressive sequence and then transgressive, regressive, okay? Going back through time, that's a transgressive sequence. Underwater again, regressive, regressive, long period of being on land. Transgressive, underwater, okay? So if I just draw this line up to Paris right now, I can see what the history is of that one location being underwater or on land. Interesting, huh? Stratigraphy, so useful, so cool, so fun. All right, that's all I got for you today. Any questions? No? Well, then I'm going to end the recording here. No new lab today.